done step 2, right here, the values that you get from setting it equal to 0, right? We would get like x equals 1 and x equals 5. Those two values, or however many values, are your critical numbers. If you take that number and you substitute it into your original equation, f of x, that will get you your y value. So your entire coordinate is your critical point. So your critical number is just the x value. Your critical point is the entire coordinate. Yep. Once you have your end coordinates and you have your critical points, then you need to set up your chart just like we did in 3.1. So you'd have your test values, your sign of f prime, and you'd have the nature of the graph. And I'm going to show you how this works in the example after, and then you're going to state your max min. So this process is very similar to what we've done in 3.1 and 3.2. The only difference is that you're working with the f prime. So when you look at this graph here, it's all the same. You have your test values. You would have your intervals that you're working with, right, depending on what those intervals are. And then you have your sign of f double prime. That's the only difference. This is not f prime anymore, it's f double prime. And then you're still able to say the nature of the graph. So I'll go through them again. You first have to determine all your derivatives. The only reason you have to find f single prime is in order to find your double prime. Then you want to set your double prime equal to 0 and solve for those x values. Then you create your table just like we did before, this being the only difference. And then you would state your intervals. These will be your intervals of concavity. So if we already know the critical numbers from before, if we are to look at absolute max and absolute min, the way I say it is that is absolutely the highest or lowest spot. Do we have a point on this that is the absolute highest point? For example, if you had a graph where it kept going infinity in either direction, is there ever going to be an absolute max or an absolute min? No, because it's going to keep going. And infinity is not an absolute value. So that has no absolute max or min. But this one does. It has it here. This is an absolute max. Do we have an absolute min? Yep, right here. This is the lowest spot. We have a local max. Yeah. This one here. Perfect. So this is a local max. And then likewise, same idea. This is a local, so right at the bottom, min. It is a low spot, but it's not the lowest spot. So if a local extrema is a turning point, that's going from a positive slope to a negative slope. So any max or min that you come to, that will be a local extrema. So it's just a local max or a local min. So let's try this example here. This is different than the example that you did from the textbook. The example that you did from the textbook, it took your two endpoints, and it took your critical points, and it subbed each into the f equation, so you had coordinates for every single point. And then from there, you picked the highest values. Those were your absolute. And then your middle ones, you had to figure out whether they were local max or min. So this is another way which I think visually shows you the local max or min. The only problem is it doesn't tell you for sure if it's an absolute. So now that you have your derivative, step 2, set it equal to 0. And if we set this equal to 0, we can't solve it like we did in 3.1. What do we have to do here? Could do synthetic. So we're factoring. What's the first thing you should always look for when you're factoring? What's common? And we have an x squared common here. So we now have that x equals 0 and x equals 6. Those are your critical numbers. Not your critical points, your critical numbers. Can you figure out what your critical points are? Yeah. You just take that and you sub it into your f, your original equation, to get the critical point. If we're setting up our chart, we still have test values, the sign of f prime, because maxima and minima are still f prime, and then you have the nature of your graph. And what would our intervals be if these were our two critical points, or critical numbers, sorry? Negative infinity to 0, 0 to Good. And 6 to infinity. And there would be your table. So let's figure out test values. What's the possible test value? Perfect. And here? Here? Perfect. If we sub those into our f prime, what sign do we get? So if we are decreasing, decreasing, increasing, the way this helps us find our local max or min, if you look between decreasing and decreasing, you can't tell anything because you're always decreasing. But when you look between decreasing to increasing, what do you have? Local max or local min? You have a local min. So just looking at the intervals of increasing or decreasing, that tells you whether you have a local max or a local min. So you have a local min at x equals 6. All right, so part C. So once you have your f double prime, what do you do? Same as before. Yeah, set it equal to 0, and then you want to do your factoring. So if we make our chart, we'd have our test value, we have our sign of f double prime, and we have the nature of our graph. What are our intervals? 2? Good. 2? Good. Which is what mean? Okay, so if we sub in that -1, what sign? We are subbing into f double prime. Positive or negative? Positive. If we put in 1, 5. Okay, good. Again, the textbook subs in 4 and subs in 0. You know that those are already 0. I'm not expecting you to waste your lead to write, again, that they would equal 0. You can say your concavity. If it's positive, the concavity is that it opens up. If it's negative, the concavity is that it opens down. And so the question asks you to state your intervals of concavity. So just like you did with the increasing and decreasing, you say, therefore, the concavity is it opens up between negative infinity to 0, as well as 4 to infinity, and it's concave down from 0 to 4. So since the point of inflection is a change in concavity, we also have, therefore, the point of inflection, they are at x equals 0 and 4. That helps us explain this, though, because when we went again with our second derivative, here, we didn't know what was happening, right? We had a decreasing and a decreasing. How does that make sense to also have a point of inflection? Well, let me add a page. How that makes sense here is a point of inflection can be something like this. So all along here, you are concave down. And then you get to this spot right here, and now it switches to concave up. So that is a point of inflection. But if you look at the slope, no matter where you are, the slope is still positive. So it's not a maxima or a minima, or maximum, local max, local min, but it is a point of inflection. There is a change in slopes there, or in concavity. So if you set up your table here, your table, you can have a test value, but we are only testing 0 and 6, because those were our critical numbers back from part A. If we hadn't have done part A, you would have had to find f prime, set f prime equal to 0, and find these values. So we are figuring out the sign of f double prime, and we are figuring out the nature. That this is a point of inflection, and this is a local min.